Namaste, hello everyone, welcome to this session. So, in this session we are going to solve some examples on the topics we studied in lectures 23 to 25 of this course on experimental mode analysis. And the topics we covered in these lectures are FRF estimation, H1 and H2 estimates of FRFs, coherence function, test planning for FRF measurement and FRF measurement with an impact hammer. So, you can see that all these topics are strongly related with the measurement aspects, measurement of FRF, right, and that involves also subsequent data processing, estimation and computation. So, it is really difficult to have some numerical classroom like problems on the topics. However, I have designed some examples to reinforce some of the concepts we studied in these lectures. Of course, in the assignments you will find several multiple choice questions to test the understanding of the concepts we learnt in these lectures. Please watch these lectures to learn the background theory behind the examples we are going to solve in this session today. So, let us get started with this session and solve example number 1. So, I go to next page. So, let me write the question first. Example 1, question: in an impact hammer test, the accelerometer is kept fixed at test point 3 and FRFs at all the test points are measured by a roving hammer test. List all the FRFs that will be measured if there are 5 test points, right. So, let us solve this problem. So, just like in a roving hammer test, as we explained, as we studied in the lectures, the accelerometer is kept fixed at a particular point, at particular test point, and then the FRF is measured by applying impact on the structure using an impact hammer, right, in sequence, right. So, we apply at one point, we measure the FRF, then move and then we move to the next point, right. So, the impact is applied at in the next point. So, in this way we cover or row the hammer from one point to next point in order to measure all the FRFs. This already we discussed in the lecture classes. So, in this question basically what has been asked is that if there are 5 test points in the accelerometer has been fixed at test point 3, then what are the FRFs that will be measured. So, just to further give the insight, what we do is that if we have 5 test points, then we will have essentially we can have 5 into 5 FRF matrix. So, if I show that a 5 by 5 FRF matrix in this manner, then I will have alpha 1 1, alpha 1 2 going up to alpha 1 5, right, like this. Then alpha 2 1, alpha 2 2, alpha 2 5, then we have alpha 3 1, alpha 3 2, alpha 3 5, right, and then at the end we will have alpha 5 1, alpha phi 2 and alpha phi phi. So, this is the FRF matrix, correct. And now if accelerometer has been fixed at point number 3, right, and the hammer is moved to other test points. So, we know that the FRF is designated as alpha j k, right. That is how the FRF is designated, where j is the response point, right, response degree of freedom or test point, whatever you want to call it, right, and k is the I think I need to correct this, response, right. K is the excitation or force DOF or test point. So, with this nomenclature, if we have accelerometer fixed at test point number 3, then obviously we will have the FRF measure will be, and if let us say if apply the impact at first test point, then it will be alpha 3.1, and then we move to second test point, it will be alpha 3.2. So, this basically shows that this third row of the FRF matrix we will be measuring, right. So, essentially we are going to measure this third row of the FRF matrix. This is the third row of FRF matrix. So, therefore, we can simply say that the FRFs that will be measured will be the FRFs that will be measured in this test will be alpha 3.1, alpha 3.2, alpha 3.3, alpha 3.4 and alpha 3.5. So, these 5 FRFs will be measured. So, this essentially completes the solution of example number 1. Let us go to next example. So, this is example 2. So, the question is something like this. The figure below shows a sketch of mode shapes, right, sketch of mode shapes of a fixed beam right, a roving hammer test is to be performed on the beam to identify a model comprising of first 4 modes of the beam, right. So, the first part of the question is what are the test points. So, I think one more line I forgot to write here, that the test points used for measurement are also shown, right. So, the part A of the question is what are the test points which are not suitable for choosing choosing the location of a fixed accelerometer for the test, and B is which points are more suitable. Right. So, this is the thing, and now let me show the mode shapes which are being given here. So, this is the beam like this, right, and this is a fixed beam, and so the points which are given are this 3, then 4, 5, 6, 7, right. So, this is the actually this is the fixed beam like this, and then we have point 1, 2, 3, 4, 5, 6, 7, right, and the mode shape, the first mode shape is something like this. Trying to roughly sketch it like this. Is the first mode shape. Then we have the second mode shape here, which is given, and here this is the second mode shape, right. Then we have third mode shape, this is third mode shape, right. Maybe also I can indicate the test points. Maybe I can do that later. Let me first complete the plot of mode shapes, and this is the fourth one. Okay. So, this is the that is the fourth mode shape, right, and these are the points basically. Let me also show the points here, the test points. So, this is again I can, if I number them 1, 2, 3, 4, 5, 6, 7, right. Similarly, I can, this one is third mode shape, okay, and the points are 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 7, right. And then I have the second mode shape here, right, and this is the point, and then I have 1, 2, 3, 4, 5, 6, 7. Great. So, these are the essentially the mode shapes being given to us, and first mode shape. Let us solve this problem. So, part A. So, by looking at these mode shapes, we are supposed to identify what are the test points which are not suitable for choosing the location of fixed accelerometer in the roving Hamel test. As we know that in the roving Hamel test, the response transducer, the accelerometer is kept fixed, right, and the hammer is rolled. So, what would be the most the points which are not suitable for selection or mounting the accelerometer. So, as we explained, as we studied in the lecture classes, the accelerometer location should be such that all the modes we want to measure, they must be observable from that point. Observable means that the mode shape should have non-zero displacement at that point. So, if the location of the accelerometer coincides with any of the nodes of a mode, right, then that mode will not be measurable or observable, right, from that location of the accelerometer. So, that is why what we should do is that we should look at each mode shape and identify the points which basically coincide with the nodes of that mode, and those points then are not suitable for measurement for those modes, right. So, let us do that. So, first we write down the point which is not suitable. So, if I write here mode, and here if I write the node of that mode, right, and then we can write our comment here like this, okay. So, therefore, if I write the first mode here, then mode number 1, then mode number 1 you can see it has no node, it is a fundamental mode, right. So, all points are okay for this mode. So, we will simply say that there is no node, nil, right, and then all points are suitable. So, all points are suitable, at least from this perspective, right. Among them again we can have our preference, right. Then let us look at mode number 2. So, for mode number 2, there is node at 4. You can see at test point number 4, this mode, second mode has a node. So, if we mount accelerometer at point number 4, then the second mode will not be observable, it will remain unmeasured in that FRF, right. So, therefore, this mode will not be captured. So, this is not suitable, not suitable location. Then if I look at 3, then again here the nodes, they do not coincide with the test points, right. So, there are 2 nodes this mode has, and those 2 nodes do not coincide with any of the test points. So, nodes we do not have any node coinciding with the maybe I can write here there are 2 nodes, maybe I can rather I would say that this node here is actually coinciding with test point. that would be more appropriate to write. So, here we are only listing those nodes which are coinciding with the any of the test points. So, here for node 3 there is no node coinciding with any of the test points, so we will say all points are suitable. Then at the end we have mode number 4, and here we see that we have in fact the 3 like 2 and 6, correct. So, we have 2, 4 and 6, there are 3 points, they are these points not suitable, locations, correct. So, therefore, this shows that the test points 2, 4 and 6, they are not suitable locations, okay, for measuring the first 4 modes. So, what is our conclusion? That test points 2, 4 and 6 are not suitable choices for mounting the accelerometer. Correct. So, now the next part is that which points are more suitable. So, let us do that. Which points are more suitable? So, the all remaining points, at those points if you mount accelerometer, all modes would be observable, correct. But again among them what we see is that maybe the points which are close to the fixed ends, there the amount of signal may be smaller as compared to the points which are away from the fixed end. So, signal to noise ratio may be an issue at points which are very close to the fixed end, right. So, maybe we may not prefer those points, that could be one way to look at the choice, right. So, so the points which are more suitable are, therefore, we can have point number 1, maybe 1, then 3, then 5 and 7, right. These are the possible choices, and among them point 3 and 5 would be better, right. 3 and 5 would be better from the perspective of signal to noise ratio, right. They are preferable, they will have higher signal to noise ratios compared to 0.1 and 7, right. So, in this way I think we complete the solution of example 2. Now, we go to example 3. So, example 3, let me write the question. FRFs over a frequency range of 1.6 kilohertz, right, are to be measured on a structure. Structure using an impact hammer test. A frequency resolution of 0.25 hertz is required. Find the relevant time and frequency domain parameters of measurement. Okay. So, let us solve this problem. What has been given? We have been given f max as 1.6 kilohertz, which essentially means 1600 hertz, and we have been also asked to have a frequency resolution of delta f, which is 0.25 hertz. That is the frequency resolution that is desired, right? And now we have to find the other parameters of the time and frequency domain. So, in this problem you see that what has been given is that we have to perform the measurement on a structure, correct, and with the frequency range of 1.6 kilohertz. This structure, being a continuous structure, what may happen is that when we apply the force itself may have frequency components beyond 1.6 kilohertz, and the response also may contain frequencies which are beyond 1.6 kilohertz, isn't it? So, in this situation therefore, in order to avoid aliasing, we will have to first pass the signals which are measured, the force and response signal, through anti-aliasing filters. So, here we will have to use anti-aliasing filters, correct, so that we remove all the components which are beyond 1.6 kilohertz or beyond the cutoff frequency of the anti-aliasing filter, and then we do the discretization and then the measurement, and this would ensure that there is no aliasing of the signals or the components which are beyond frequency range of measurement. So, here now let us choose now this time and frequency domain parameters. So, as we studied in the lecture, the sampling frequency we will take as 2.56 times f max, and that will be 4096 hertz, right. And then the cutoff frequency of the anti-aliasing filter would be fs by 2, and that would be 2048 hertz. So, the other way to look at this thing is we can also say that alternatively that the cutoff frequency of the anti-aliasing filter is 1.28 times the maximum frequency range. So, we are removing all the components, we are trying to filter out all the components which are beyond 1.28 times f max, and this is 2048 hertz. And now, since after filtering we are left with frequency components from 0 to fc, that is the 2048 hertz, then in order to avoid aliasing we must choose the sampling frequency in accordance with the Nyquist sampling theorem, which says that we must take the sampling frequency at least twice of the highest frequency component, which is fc in this case. So, therefore, then we can say that fs will be equal to twice of fc, right, and that gives us 4096 hertz. So, that basically is the choice of the cutoff frequency and the sampling frequency. Now, once this is done, now let us look at the other parameters. The other parameters would be, say, the time resolution or time step, that will be 1 upon fs, and that would be 0.000244 seconds, correct. Then we have the number of samples NT, that will be equal to the record length upon maybe I think first we can determine the record length, correct, and that would be equal to 1 upon delta f, and that would be then 1 upon 0.25, which means 4 seconds, and then we can determine del nt, the number of samples in the time domain, that will be equal to t upon delta t, right, and that would be 16384. Let me rewrite that. 16384, and number of frequency lines in the single sided spectrum, right. This is number of frequency lines in one sided spectrum. They would be equal to f max divided by delta f, which is 1600 divided by 0.25, that is 6400 lines, right. So, this is how we can compute the all time and frequency domain parameters. So, this complete solution of example 3. Let us go to example 4. Let me go to next page. Example 4. Question is something like this. FRF measurement on a beam is to be performed. Okay, performed under free boundary conditions, right. The beam is suspended from a rigid ceiling using two elastic bands to simulate free boundary conditions. Okay. Find whether the suspension is appropriate to simulate free boundary conditions for the test. The lowest flexible mode of the beam has natural frequency of 12 hertz. Okay. So, let us look at the solution of this question. So, essentially now if you look at just the sketch of this. So, this is the rigid ceiling and this is the beam under test like this, and it has been suspended using elastic bands like this. Okay. So, these are the elastic bands, and it is given that the stiffness of this band is 20 Newton per meter, that is given, and this is beam under test and this is rigid ceiling. Okay. And also the dimensions of the beam are given. The properties of the beam are the length, these are beam properties, and what are they? The length of the beam is 0.4 meter, the width is 0.05 meter and thickness is 0.005 meters, and the density of the beam material is 7800 kg per meter cube. So, this is all given. So, in this problem you see situation is described where the beam is to be tested under free boundary condition. In the lecture classes we studied different boundary conditions which are used for model testing. Free is one of them, it could be fixed or it could be in situ model testing. So, free is a condition that is typically simulated because free means there are no restraints on the structure, as we studied in the lecture that there are no restraints, and obviously, but then you need to support the weight of the structure during test. So, therefore, what is done is that we use very soft supports. One way to do that is to suspend the structure using very flexible strings, flexible elastic bands, so that structure can just vibrate the way it wants, right, no restrictions on the structure. So, now the question is that what should be the stiffness of those elastic bands, and in this question what has been asked is to determine whether the bands which have been used, which have the stiffness of 20 Newton per meter, there are two of them, are they good enough or are they appropriate, and would they allow a reasonable simulation of free boundary condition for the test. So, as we discussed in the lecture class, one of the guiding principle is that the stiffness should be such that the first rigid body mode of this suspended structure, it should be less than 10% of the first flexible mode natural frequency. When that happens, then the stiffness of the bands will not interfere with the dynamics of the structure, those modes, right. Otherwise, if the stiffness is higher, right, if this stiffness is higher than the making the first rigid body natural frequency closer to the first flexible mode natural frequency, then the natural frequencies themselves may get altered in some manner, right, and then we will not be able to estimate the correct natural frequencies or the modes of the structure under free condition. So, let us determine what is the rigid body natural frequency. So, let us determine first of all the rigid body mode, rigid body mode natural frequency. Let us determine that, because we have been given the flexible mode, the first lowest flexible mode that is given. So, we should determine what is the rigid body mode natural frequency with these suspensions. So, of course, the mass we can determine of the structure from here, which is simply L into W into T, right, into rho. So, if you do all this, then you get 0.78 kg, correct, and therefore, the natural frequency, rigid body natural frequency, if I call it the omega r, and that would be equal to the equivalent stiffness of the bands, which will be 2K, because those the bands provide stiffnesses which are in parallel. So, it will be 2K divided by m, right. So, which means 40 divided by 0.78, and that gives me around 7.16 radians per second, and in terms of the hertz this is around omega r upon 2 pi, and that is 1.14 hertz. So, that is the rigid body natural frequency. So, you can see the structure is obviously because of very soft bands, it is going to just vibrate very slowly, just completing little more than one oscillation in 1 second. So, that is pretty low, right. But then whether it is good enough or not, that we will find out by comparing this with the lowest flexible mode natural frequency. So, if I now find the ratio of Fr with the natural frequency, the first flexible natural frequency, then that is around 1.14 divided by 12, right. So, this is around 0.095. So, this essentially means that the Fr is less than 10% of Fn, right, okay. And therefore, this suspension with this stiffness can be considered suitable for simulating free boundary condition for the test. Hence, the suspension can be considered adequate to simulate free boundary conditions for the test. So, I think in this way we complete solution of example 4, right. So, today we solved this session 4 examples. So, I think now we can stop here. Dhanyavad. Thank you.